This is about integration in NMR. And integration really is the way that we find out how many hydrogens are in a given environment. So first, when looking at a molecule like this, we need to identify the total number of environments present, unique environments. So this position is unique, this position is unique, this position is unique. In other words, 3 different spots, you expect to see 3 different signals. In this molecule, the methyl is unique, but then each of these 3 is going to be in the same environment. There's a local plane of symmetry right there. So anyway, all 3 of these will occupy the same environment. And that has implications for what the signal looks like. Acetone, because there's a plane of symmetry running right down the middle of the molecule, you expect these 2 to have the same environment. Those 2 hydrogen groups to be in the same environment. We can run the same mental thought process when we're looking at carbon NMR. So if you look at this carbon NMR right here, this is a benzene ring. What you need to keep in mind is that the benzene ring has a resonance form where the double bonds are on the other side. And what that means is the actual resonance hybrid for benzene essentially looks like a ring with a ring of charge. Said another way, each carbon in a benzene is the same. So there's a single carbon environment in a benzene. We have 1 carbon environment right there, 2, that's unique because the methyl is bound, but then these are both the same, these are both the same, that one is unique. Plane of symmetry, but there's also a plane of symmetry that runs this way. So if we're trying to decide how many unique positions there are in the molecule, the methyl itself is unique, that's position 1. Where the methyl binds to the ring is unique, that's position 2. But then this is the same as this because of the plane of symmetry, but it's also the same as this because of the plane of symmetry, which is the same as that. Once you've decided on the number of unique positions in a molecule, then you can start to answer the question, how many hydrogens are in that environment? So with this molecule that has 3 unique environments, it's easy. There's 1 hydrogen. So when I do the integration, that will be 1H. Here, there are 2 hydrogens. When I do the integration, I should see 2H relative to this. And then there are 3 hydrogens on the methyl, so that would be 3H relative to the 2H relative to the 1H. Integration is both relative and absolute. In this case, we have relative integration of 3, 2, 1, but that also serves as the absolute integration for the molecule. Here, how many hydrogens do we expect to see at this methyl? 3H. These 3 methyls are 3H each, with a total of 9H in this environment. Overall, this will be 9H in that environment. And so here you can see a relative integral of 1 to 3, but the absolute integration will be 3H and 9H. We have 2 3H signals, but because of the plane of symmetry, they end up as the same. That is a 6H overall. I'm not interested in the proton environments here. When I'm looking at the carbons, what you see instead is that there are 6 carbons in a single environment. Here, we expect to see 1, 2, 3, 4, 5 environment, but what we'll see is 2 carbons in a single environment, 2 carbons in a different environment. In carbon NMR, we do not do integration. Instead, we sometimes get to take advantage of intensity. So what do we expect to see for this molecule? We expect to see 1, 2, 3 carbons that will all be the same size. So a relative height of 1 to 1 to 1. But then environment number 3 has 2 carbons in it. We expect that to be twice as tall. And environment number 4 has 2 carbons in it. We expect that to be twice as tall as environments 1, 2, and 5. So intensity, the height of a carbon NMR peak, is information that essentially correlates with the integration in proton NMR. For this molecule, we have 2 carbons in environment 1, 2 carbons in environment 2, and 4 carbons in environment 3. So our intensity ratios that we expect are 1 to 1 to 2, or perhaps in an absolute sense, 2 to 2 to 4. Integration, again, is really about understanding how many carbons or hydrogens are in a given carbon or hydrogen